So one thing to notice with nuclear reactions is that any atom that has more than one proton, so anything other than hydrogen, is going to have repulsions between those protons in the nucleus. So what's actually holding any of these protons together is called the strong nuclear force, and it is a really high amount of energy because it allows these protons, these positive charges, to stick together and form the nucleus. So that is the basis of nuclear energy, is harnessing the force that's in the nucleus. So how do these nuclei stay together, especially ones that get so big? Well, the answer is neutrons. Neutrons really help to stabilize the nucleus and these protons being stuck together. And as you get more and more protons, so as you increase your nuclear charge, you're going to have even more and more neutrons that are needed. So initially what you'll notice on the periodic table is if you look at something like carbon. Okay, right, carbon has 6 protons, and you can see based off of a carbon's atomic mass, right, the average on the periodic table, it's like 12.01 AMU, which means that 6 of those AMUs come from the protons, so therefore the other 6 must come from about, on average, 6 neutrons. So initially, when we have our earlier atoms from about 1 to 20, we're pretty stable with 1 neutron to 1 proton, so the ratio being 1 to 1. As you get to become a larger element, you're going to need more neutrons to help you stabilize. So approximately once you get to the number of about 40 or 20 to 40 protons, you have about 25% more neutrons in there. So the ratio being about 1.25, so a little bit more. Once you get from 40 to 80, you're going to increase even more. So you can see from 40 up to 80, our slope increases even more, and your ratio for stable nuclei is about 1 proton to, well, about 3 neutrons for every 2 protons, so 1.5. Now, we're not going to memorize these numbers. In the past, I would have had you memorize them, but I don't find them super helpful. Just know that as you get more and more protons, you're going to need more neutrons to help stable out. And that's going to continue to increase as the number of protons increase. And in fact, any nucleus that has more than 83 protons is not stable. So that's anything above lead. So what we're going to do to determine whether an isotope that we have has a stable nucleus is we're going to look at the average atomic mass on the periodic table and compare that to the mass of the isotope. So for example, if I had carbon-14, I would want to compare it to what I see on the periodic table. On average, carbon has an atomic mass of 12.01. So that means about 6 protons and 6 neutrons, right? So this isotope has too many neutrons. So my ratio of neutrons to protons is too high. So some of those neutrons end up getting converted into protons via beta decay. So what this guy would do is carbon-14 would end up undergoing beta decay. So we have a beta particle comes out, and I end up getting 7 and 14, and then I have nitrogen. And if we look at nitrogen's atomic mass on the periodic table, it's 14. So this guy is way more stable than what it was before. So I've really stabilized that isotope via beta decay. If my neutron to proton ratio is too low, then I need to make some more neutrons. So I'm going to take protons and convert them to neutrons. More often via positron emission or electron capture, sometimes through alpha decay, but that's not as efficient because you're losing both protons and neutrons in that way. So that normally happens with atoms or isotopes that are very large and need to undergo multiple decay. So let's practice. We're going to look at these 3 different isotopes. I have magnesium 28, magnesium 22, and molybdenum 102. So if we go go find these guys on the periodic table, magnesium has a atomic number of 12, and molybdenum is number 42 on the periodic table. So if we go compare the average atomic mass of magnesium from the periodic table, magnesium's atomic mass is 24.3 AMUs. Okay, so for both of these, it's 24.3 grams per molar AMUs. So if we look at the atomic mass number 28, well, that's way higher, right? 28 is greater than 24.3. So that means that my neutron to proton ratio is too large. So I need to get rid of some neutrons, and so I'm going to do that with beta decay. If we look at this other isotope, magnesium 22, 22 is a lot smaller than 24.3, so I actually need to make some more neutrons, and so I'm going to do that with, it says either beta decay or positron emission here, so this would be done with positron emission. All right, now molybdenum, and it's number 42. Its average atomic mass is 95.95 AMU. So if I look at this mass here for my isotope, 102 is larger than the average 95.95, meaning it's too big, so it's going to undergo beta decay to stabilize the nucleus.
Oftentimes you're not going to have just one decay happening. You'll have multiple different types of decay in series. So there are 157 stable nuclei, and those tend to have even numbers of protons and neutrons. In isotopes that have either an odd number of protons, an even number of neutrons, or vice versa, or have odd number of neutrons and protons, then these are less stable. And so in order to get the process to get to a stable isotope, we're going to have more than one transformation. So very rarely are they able to stabilize after undergoing one transformation. So they're going to undergo this series of decay, and oftentimes this will happen until you get to lead. You might wonder why lead? Well, if we look at our periodic table, that's about where we get to those. Lead has it's number 82, and remember, once we have atomic number 83 or higher, we don't have any stable. So lead's like the first element that is actually stable.